Salam everyone, welcome to Physics with Noshir Alam, and we are continuing with electricity. Now, as you all know, that electrical power P is given by the formula V into I, where V is the voltage and I is your current. Now, you also know that V is equals to IR, so P is I squared into R, and also you know that current is V over R, so we can also end up getting the relation P is equals to V square over R. Now, a very common question that you have two relationships over here, one which shows a direct relationship with R, another which shows an inverse relationship with R. Which relation is correct? The answer is that your power dissipated has to increase with resistance under all normal circumstances. जब लोड बढ़ाओगे तो पावर डिसिपेटेड बढ़ेगी. तो ये रिलेशन कब ठीक होता है? ये रिलेशन तब ठीक होता है अगर आप वोल्टेज कांस्टेंट रखें. ओनली देन पावर इज इनवर्सली प्रोपोर्शनल टू आर. सही है? सो लेट मी राइट दैट डाउन. नोट, ओनली व्हेन योर वोल्टेज इज कांस्टेंट, then your power dissipated is inversely proportional to resistance. Only then. Otherwise, no. Otherwise, in all normal cases, the power dissipated will increase as resistance increases. And energy is power into time, so you can get three formulas from here. E is equals to VIT. If you use P is equal to VI, you could get E is equals to I square RT, or you could get E is equals to V square over R into T. All three formulas can be used to find out the energy. Now, unlike O levels, you don't have to convert into kilowatt hours. So remember that V must be in volts, current must be in ampere, and the time must be in seconds, and you should be good. Alright, next. So you know that P is equal to VI, and once they asked this question of defining EMF in a different way, so what they did was they substituted V with E and wrote like this, and then obviously EMF becomes equal to P over I, which basically means that P is the power generated by the cell divided by the current delivered by the cell. Now, since we're talking about cells, we cannot ignore the internal resistance as you studied with me earlier. So every cell has its internal resistance, small r, and let's say it is connected to an external road, capital R, like that. And there is a current in our circuit going from the positive terminal to the negative terminal, and you know that this voltage is called terminal voltage because it's the voltage at the terminals of the battery, right? Now, assuming no power loss besides the power loss in the internal resistance, no other power loss, I can safely say that the power delivered by the cell must be equal to the power dissipated in small r plus the power dissipated in capital R. Makes perfect sense. There's no other power loss, assuming that the wires, there's no heat loss in them. So the power delivered by the cell is the EM of the cell into the current, EI. The power dissipated in the small resistance is given by I square into small r, and the power dissipated in capital R is given by I square into capital R. अगर आपके ज़हन में सवाल आ रहा है कि V square over R क्यों नहीं यूज़ किया, तो देख लें कि मैं करंट दोनों में सेम रह रहा है, और मैं करंट के साथ कुछ करना चाहता हूँ, तो दैट्स वाई आई वांट द होल इक्वेशन बी इन करंट। वरना वोल्टेज में वी स्क्वायर ओवर आर भी बनाया जा सकता है, वो गलती कोई नहीं होगी, बट वो प्रूव करना चाह रहा हूँ वो नहीं होगा। सो अब इफ़ यू हैव अ लुक, तो EMF is equals to I times small r plus I times capital R, and this is the equation that you have seen. If you remember, EMF is equals to I into R plus the terminal potential difference. So you've seen this before. I'm just deriving it from a different way. Now, carrying it further, I can take I common like I intended to, and I could write it as R plus capital R is equals to E, and therefore the current would become equal to the EMF divided by small r plus capital R. Now, if I talk of the efficiency of this circuit, efficiency, as you all know, is the ratio of the power output and the power input. In this case, the output is the power across the external resistor capital R, and the input is the power generated by the cell. Now, the power that is given out to the external resistance can be written as I into Vt, because that is the power across the external load. P is equal to Vi. The voltage across the external load is Vt. The current that is going is I, so I into Vt, divided by the power of the cell. And the power of the cell is given by I into capital E. EMF of the cell, capital E, current I, ये बन गया. Current is the same, cancelled. So you get Vt is equals to Vt over E is equals to the efficiency. N or eta is the so-called symbol for efficiency. Now, as you know, Vt is I times capital R. Vt, this voltage, is due to the current flowing through this resistance, so I times capital R. And what was E equal to? E was equal to this thing. So I'm going to write it down. E is equals to, because you're talking of the cell, तो cell ने तो छोटे r और बड़े r दोनों को दिया. So this cancels out. So the efficiency N or eta can be written as R divided by small r plus capital R. A very important formula, because it can they can ask you in the question, and they can ask you in the question of to find the efficiency just by giving you the value of small r and capital R, and this circuit. You can use this formula very, very easily. I now want to discuss with you the concept of power and its relation with power in relation with small r and capital R. Like, how does the power delivered depend on small r and capital R? And for that, let's just do a very quick example where, let's say I have a 12 volt cell which has a 2 ohm internal resistance, and we have an external resistor which is variable, so I can change the values. Now, let's say the value is capital R, and capital R will change from 1 to 2 to 3 to 4, and we're going to measure a couple of things. The first thing I'm going to measure is the terminal potential difference, plus and minus. I want to measure the current, so I'll put an ammeter. I wanted to measure the voltage, so I'll put the voltmeter. Voltmeter will tell me the terminal potential difference. Ammeter will tell me the current. Okay, so let's begin. So the resistance value starts from 1 and goes till 4. Let's find out the current in amperes first. So when the value of R is 1, so 1 plus 2 is 3. I want to find the current. V is equals to IR. 12 divided by 3 is 4. Next, 2 plus 2, 4. 12 divided by 4, 3. And then you get 2.4, and then you get 2 amperes. Next, let's find out what is the terminal potential difference in volts. Now, the terminal potential difference in volts is the product of the current that is going through the internal resistance through this external resistor capital R and the value of capital R. So current ये है, resistance ये है, multiply करें, voltage निकल आएगा. So the first value is 4, the next value would be 6, the third value would be 7.2, and the fourth value would be 8. All right. Now let's find out what is the power dissipated in the external resistor in watts. Power is given by VI or I square R, whichever formula you want to use, all will lead to the same answer. So let's use VI, the voltage and the current. So voltage is 4, current is 4, so you get 16. Then you get 18. Then you get, I think, around 17.3, and then you end up getting 16 again. Now, if you look at the values very closely, you will see something. Look at the power. The power increases and then starts falling. And if I ask you to tell me which is the highest power, you will definitely circle 18. And if I circle 18, then I'll say, okay, this whole row is special for me. Or ये पूरी row special क्यों है? Because there's a very big hidden message. And that is, look at the value of small r. What was the value of small r? It was 2 ohms. Look at the value of capital R. What was the value of capital R? 2 ohms. So remember that when maximum power is dissipated, that is only when the impedances match. Impedance is the technical word which we use in engineering for resistance. Power is maximum when impedance matches. Impedance को आसान अल्फाज में resistance भी बोल सकते हैं. So power is maximum when small r becomes equal to capital R, and that is something which you will never forget. That in a question, if they have given you the internal resistance and the external resistance, and they're asking you, will the power dissipated remain constant or will it change? It will change depending on the value of R. Where will the power dissipated maximum? When the value of small r and capital R become equal. And that's always going to be the case. So never ever think that it's going to change. In fact, at times they can also give you a graph to draw, or they can make this graph for you and they can ask you different questions. निशानी क्या होगी? Y axis पे power लिखा हुआ होगा और X axis पे resistance लिखी हुई होगी. Now in the entire chapter I've never mentioned this graph, but now I am. So be careful, watch out for this graph of power versus resistance, especially when internal resistance is given, because as you saw 16 से पहले वैल्यू कम होगी तो पहले वैल्यू बढ़ती गई मैक्सिमम हुई और फिर कम होनी शुरू हो गई. So the value of R was increasing throughout. The value of R was increasing throughout 0, 1, 2, 3, 4. But the power increased and then decreased. So R was increasing throughout, but the power increased and then decreased. So you understand the shape? The shape would be an inverted curve like this. And then they will ask you, what is so special about this peak? You will say, well, this peak basically shows that the power dissipated is maximum. This is the maximum power dissipated. And it'll say, okay, what is the value of the external resistance when this happens? You will say, well, the value of the external resistance is given by this value R1. And then they will say, okay, well, have a look at this and tell us what is the value of the internal resistance. You will say that the internal resistance also has the same value R1 because of this fact that I've mentioned, that power dissipated is always maximum when the impedances match. Very important concept, and if you do get a good grip on it, hopefully this will not trouble you. And two more graphs which are very important. One is the relationship between current and resistance. Now the load is going to increase because this variable उसका तो हमने बढ़ाते रहना है, but आप current को देखें, current कम हो रहा है, शुरू में तेज़ी से कम होता है, 1 का ड्रॉप आता है, देन थोड़ा स्लो डाउन करता है, देन और स्लो डाउन करता है, बट गिरता रहेगा because obviously if you keep on increasing this R, the current will keep on decreasing. Eventually at some point the current will become zero. The resistance बहुत ही ज़्यादा बढ़ जाएगी. But you know that we never touch the x-axis, so all you need to know is be mindful of the trend, that if you have a current versus resistance graph, then in that case the current will start off from some value and then it'll decrease like this. Why like this? Because initially this shows that the rate is fast, like I said, and then as you increase resistance further, it's not that fast, but it's still decreasing. And the last but not the least, how does the terminal potential difference vary as the value of R is increased? Can you guess? Well, one thing you can see clearly that it's increasing, but what's the other thing? Is the increase fast in the beginning or towards the end? What do you think? It's faster in the beginning. पहले 2 का जंप है, फिर देखेंगे 1.2 का जंप है, फिर 0.8 का. सो स्लो डाउन कर रहा है बट बढ़ ही रहा है. सवाल ये कितना बढ़ सकता है? Remember the law of conservation of energy. It cannot exceed the EMF of the cell, which is 12 volts. So yes, your terminal potential difference will increase with resistance, but it cannot exceed the EMF of the source at any cost. Eventually it will become equal to the EMF, and then that's the end of the story. And that's the point when terminal potential difference and EMF become equal, you know that the current will go to zero. All right.